Welcome back to the part 2 of cost minimization. What we have learned that our fundamental question is to minimize the cost of input, of course, by changing the input mix. Here we are taking a production process for which we have one output and two inputs, such that at least you are able to produce y unit of output. And for a particular label, we can fix y to y naught, but this can be varied also. And two techniques we have seen. One we did with brute force, we didn't use any technique, we did simple optimization, sometime we took help of graph. Second technique that we saw, that we can do graphically, and here we have x1, x2, and then we can draw isoquants like this. All isoquants will have the same slope, and these are the isoquant given. The slope is going to be same because this is going to take a particular value, and so all combination of x1 and x2 which costs a total of k would be on this particular line, and the slope is always going to be equal to minus w1 by w2. Intercept can change as we change the value of, but nevertheless this is the way isoquant would look like, and value, the total cost, is increasing as we increase the amount of x1 and x2. But on one particular line, no matter which combination of inputs we take, the total cost would be the same. And then we say that further we can draw an isoquant corresponding to, let us say, y naught, and let us say this is the isoquant corresponding to y naught. So clearly we are having cost minimization at this point, because as we move in this direction, we are able to produce y naught, but at higher cost because we are hitting higher iso cost line. But at this point, once we reach to this point, we cannot move in this direction while maintaining the level of output at y naught. So at this point, production will take place, and the characteristics of that point is that the slope of the isoquant, which is MRTS, is equal to the slope of these iso cost line, and this is equal to minus W1 by W, or MRTS is minus MP1 divided by M. This will get cancelled, and this is, we can write it as MP1 divided by W is equal to MP2 divided by, and this has a nice interpretation that we can understand. So if we take 1 unit of input, it will cost us W1 and it will increase the production by MP1. So in other words, if we spend 1 rupee on input 1, its contribution is going to be MP1 divided by W1. Why? Because in 1 rupee you can get 1 by W1 unit of good one, and the marginal contribution is MP1. So the total contribution from 1 by W1 unit of input 1 is going to be MP1 divided by. In other word, we can say, or we can say, if 1 unit of input 2 will cost you W2, the marginal contribution is MP2. So by the same logic, 1 rupee spent on input 2 will increase the output by MP2 divided by W2. How should you spend? I can rewrite it here as it's hidden, MP2 divided by W. As which technique should we use? Should we spend a rupee on input 1 or should we spend a rupee on input 2? Of course, whichever is more. If MP1 divided by W1 is greater than MP2 divided by W2, that extra rupee should be spent on input 1. If opposite is true, if this is the case, then we should spend that extra rupee on MP2 divided by we should spend that extra rupee on input 2. So, if we are spending our money on both the inputs, what it means, they have to be the case has to be MP1 divided by uh, MP1 divided by W1 is equal to MP2 divided by W2. Let us understand slightly differently. Let us say that MP1 divided by W1 is greater than MP2 divided by W2. We should spend that extra rupee. But typically what's happening here, and we will see later on, that typically MRTS changes. If you have a more of a good, its value in production becomes less and less, and we are going to learn about it clearly. So typically it changes. There could be special cases where MP1 and MP2 are not changing ever. So we will take a look at those special cases and to understand it better. In most of the cases, as we change the level of inputs, the MRTS changes, and that takes advantage here, that is taken advantage of here. So here, if both inputs are being used, it means a MP1 divided by W1 is equal to MP2. Right? So let us look at Cobb-Douglas function, and this time we will say that minimize W1 x1 plus W2 x2 with respect to x1 x2 such that y is less than x1 to the power 1 by 3, x2 to the power 2 by 3. It means if we look at a particular isoquant, what we have is x2 2 by 3, and we can calculate MRTS, marginal rate of technical substitution, which is MP1 divided by MP2 we had obtained in previous videos, and MP1 is nothing but minus 1 by 3 x1 to the power minus 2 by 3 x2 2 by 3 divided by 2 by 3, because now we are differentiating it with respect to x2 while keeping x1 fixed. This is going to be 2. This will get cancelled. So this is equal to minus x2 by 2. And how much is the slope of isoquant? The slope of each isoquant is minus W1 2. And so from here we can obtain minus W1 divided by W2 has to be equal to minus x2 divided by 2x1. So minus minus will get cancelled. So x2 is basically W1 divided by W2 multiplied by 2. So we got x2 as a function of x1, and that again we can use this particular, because we have to produce at least y0. So we can get the amount of x1 by plugging the value of x2 from here to here. So y0 is equal to x1 to the power 1 by 3 multiplied by W1 divided by W2 to power 2 by 3 multiplied by 2x1 to the power 2 by 3. And so what do we get? 2W1 divided by W2 to the power 2 by 3. Here x1 to the power 2 by 3. Here x1 to the power 1 by 3. So this is going to be equal to x1. So from here we figured out how much is x1, which is a function of y0 divided by 2W1 W2 by 2. And similarly, we can obtain x2. We can put here a star to indicate that this is not just any x1 or x2. This is the optimal amount of input to minimize the cost when we have to produce at least y0 amount of output and 1 unit of input 1 costs W1 and 1 unit of input 2 costs W2 in the market. And cost is of course going to be W1 X1 star, W2 X2 star. So, when we write X1 star, it is a function of, we can say further, that W1 X1 star is a function of W1, W2, Y. It's of course for Y naught. When we do for Y1, there will be different. So basically, it's a function of Y plus W2 X2 star, W1, W2. And that's what we will. So this is the cost that we are getting, and this cost is going to be optimal cost star, we can say. It's going to be a function of W1, W2 and Y. Why? Because it's a function of W1. X1 star is in turn function of W1, W2 and Y. And similarly, X2 star is again a function of W1, W2 and Y. So the optimal cost is going to be a function of W1, Y, and we will come back to it. So this is much more cleaner, much more simpler to obtain than the earlier technique that we had used. But we have to be careful. Let us say if we have simple linear function, we want to minimize the cost W1 X1, W2 X2 with respect to X1 and X2, and we have done this problem such that, let us say, X1 plus X2 is greater than or equal to Y. So linear production technology. If we obtain the MRTS, how much is MRTS? MRTS is minus MP1 divided by MP2. How much is MP1? It's equal to A, which we have taken here as 1. So minus 1 divided by 1. And how much is the slope of the isoquant? That is minus W1 by W. What do we get here? W1 by W2 minus is equal to minus 1 by 1. This will get cancelled, and from here we get W1 by. But notice that W1 and W2 are not in control of the producer, is not of control of firm, is not of control of seller, because W1 and W2 are prices that these firm takes as given. They are purchasing input from the market. So it's meaningless to say that W1 is equal to W2. So what are we doing wrong? And if we look at graphically, then we would understand what we are doing wrong. But if we just plainly use mathematical formulation, then we get into trouble. So sometimes it's good idea to mix these technique and understand, and with experience you would figure out that which technique is better for which particular kind of a problem. Here is x1, this is x2. Let us say you have isoquants. Are the isoquants parallel? And when we take a linear production technology, how would it look like? It may look like, let us say, it may look like this. Now at this point or this point, where the production should take place, because if we pay attention in this direction, cost is. So we want to keep producing this output Y naught at lowest cost. So that clearly is happening here. And at that point, the slope of the isoquant, that this is the isoquant, and the slope of the isocost line, which is this one, they are not. So the tangency criteria is not being satisfied. We say we have a corner solution. And tangency criteria, we can say tangency criteria is not satisfied. And that's why we get into trouble. trouble. Of course, there are pure mathematical way to deal with such problems, but here a mix of graphical and calculus based technique help us greatly. I would again caution you differently, because if you take a look at the Leontief production technology, let us say, of course, the production technology has the form if isoquant has AX1, BX2. This is, let us say, this is a line AX1 is equal to BX2. So this is the way an isoquant look like. This is the way an isoquant look like. But we should have just one isoquant. Okay, and we should have a map of isocost line to see how do they look like. This is the isocost line. Okay, so here is x1, here is x2. In this particular case also, we see that tangency criteria is not satisfied, as that for isoquant at corner point, the MRTS is not properly defined. Let us look at how much is the MRTS on this arm, horizontal arm. If we keep x2 fixed and we keep on, oh sorry, for horizontal arm, we are keeping the x2 fixed and we keep on increasing x1, but output doesn't change. So MP1 is equal to 0. And on this vertical arm, MP2 is equal to 0, because we keep x1 fixed at, let us say, x1 naught, and we keep on x2 increasing, but there is no increase in output. So MP2 is equal to 0. So when we are calculating MRTS, we have minus MP1 divided by MP2. So on this arm, MRTS is going to be infinity, and on this arm, MRTS is going to be equal to 0, and at corner point, MRTS changes abruptly. So it doesn't make any sense. But as we had the logic last time, using logic, we can very clearly obtain that solution is going to be on the corner. There is no point wasting some of the resource. So you have to be careful about all these. Of course, in calculus, there is a first order condition, second order condition, and there are many other techniques to take care of. They are slightly more complicated. Rather than getting into a mathematical solution, we will take help of our economic intuition to understand the issues inherent in such problem. So I hope if we give you a production function, you can do cost minimization easily.